stopping me, but that's okay as well. Minimize this. Yeah, thanks very much for the nice introduction, and thank you, Gavin, for your nice talk as well. I think you convinced me that Bayesian optimization is the way forward a few years ago when I saw you speak, so it's nice to see you give an update on it. So yeah, my name is Philip Cardiff, and I'm an assistant professor in University College Dublin. I'm going to start this presentation just with some OpenFOAM related trivia. So this is the island of Ireland, and this is Dublin Bay if we zoom in. So if you're familiar with Dublin, UCD is in the leafy south suburbs. Dublin itself is partitioned by the River Liffey in the centre, and then also further by the Grand Canal to the south and the Royal Canal to the north. This is my house up here. It is not to scale, but probably Ireland's most famous mathematician was Hamilton. So in the early 1800s, he was walking from his townhouse in Dublin City along the banks of the Royal Canal out to an observatory called Dunsink Observatory, which is still there today. But on the way, when he was passing what's known as the Broom Bridge, he discovered how to multiply quaternions. So he carved it into the bridge, as the story goes. So there's a plaque commemorating that today. Why is that of interest to OpenFOAM? Well, in his development of quaternion mathematics, he was the first to propose the use of this what became known as the Hamilton operator, or the Dell or Nabla operator, so this upside down triangle. When he first drew it, he drew it sideways, but later it took this orientation. As a father of two young children working from home, I can only guess that also it was the motivation for Tinky Winky as well. I am the chair of the current OpenFOAM workshop committee, and I will be hosting or organizing the upcoming 16th OpenFOAM workshop. So I just take this opportunity to advertise that to all the attendees. Abstract submission closed just on the weekend, but it's secretly open. So if any last submissions want to come in, you can still submit them via the website. So if you go to openfoamworkshop.org. Most of this presentation, I'm going to focus around a recent article myself and Ismet Demirzic published called 30 Years of the Finite Volume Method for Solid Mechanics. So though this recently appeared online, so you might want to look it up with some nice bedtime reading. But like that article, I'm going to start this presentation with a quote from Brian Spalding. So he would be, let's say, a grandfather of modern CFD. So a quote, the late Brian Spalding. So his quote, he says, "Now, however, I recognize the finite volume method, finite element method dichotomy as being comparable with those between Protestant and Catholic or Sunni and Shia. That is to say that it promotes needless conflict and expense and loss of opportunity." So what he's saying here is essentially there's this needless conflict between finite volume and finite element. Typically people, as in most attendees here, I imagine, are, let's say, are finite volume people or fluid people. And there's maybe a wariness or a fear about what finite element does, or there's a lot of perceived false ideas about the differences between, and equally from the other side in terms of people who are, let's say, finite element people. So hopefully I'll dispel some of those myths in these slides. So to begin with, I'll just talk about the differences between solids and fluids, or ideal solids and ideal fluids mathematically. So as hopefully many of you are aware, the governing equations for an ideal fluid, so a Newtonian fluid, are the Navier-Stokes equations. So we can see conservation of linear momentum here, and conservation of mass, so in compressible form. So if we look at the governing equations for solids, they're the same. So we don't call them the Navier-Stokes equations. Navier-Stokes is only going to apply to fluids. We just call them conservation of momentum and conservation of mass. So they're the same equations. Solids and fluids are governed by the same fundamental equations. So what's different? Well, a Lagrangian approach is when we move the mesh at the same speed as the same velocity as the underlying material. So if I move the mesh in a fluid analysis at the same velocity as the underlying material, then it automatically will satisfy continuity
and the convection term will drop out of the momentum equation. So that is called a Lagrangian approach. When the convection term is still present, it's called an Eulerian approach. So Eulerian versus Lagrangian is not the same as fluid versus solid. So you can adopt a Lagrangian approach for fluids, like in creeping flow, and you can equally adopt an Eulerian approach in solid analysis. So these are not characteristics of solids versus fluids. These are just modeling approaches. Equally, Eulerian versus Lagrangian is independent of whether it's finite volume or finite element. And so all of these concepts are independent, and you can combine any of them together. You can have a finite element Eulerian fluid approach if you want. And equally, you can have a solid mechanics Lagrangian finite volume approach. So to close the equations, if we look at the definition of stress, so for an ideal Newtonian fluid, we can define the stress tensor in terms of a viscous stress and a pressure stress. And this viscous stress is given in terms of the strain rate tensor, and that's proportional to the gradient of velocity. I'm using V here because I'm fundamentally a solids guy, so that's what we call velocity, not U. An ideal solid actually has the same form of equation. The equation still looks the same. The only difference is instead of the gradient of velocity, it's the gradient of displacement. So stress in a solid depends on how far you move, where stress in an ideal fluid depends on how quickly you move. So that's the fundamental difference between ideal solids and ideal fluids. And typically in solid mechanics analysis, though not always, we will define the pressure in terms of the displacement field itself. So we won't have it as an independent variable, though it can be treated as one. And also this strain rate tensor, we actually call this epsilon. So it's just a strain tensor. So we call this strain. So what about finite volume versus finite difference versus finite element? Well, finite difference came first. And finite volume method is just a generalization of the finite difference method in terms of geometry and topology. By geometry, I mean that you can have complex shaped cells, and topology, it can be connected to an arbitrary number of its neighbors, unlike the finite difference method. So it's just a generalization. However, the philosophy of the two methods is very different. So the finite difference method takes your partial differential equation and it applies it at each point in your grid. And it tries to discretize this differential form directly at each point. In contrast, the finite volume method will take the integral form and it tries to balance this equation over each of these control volumes. So on simple grids, finite volume method is reduced to basic finite difference schemes, but they come from very different philosophies. They're trying to do it in very different ways. The finite element method then does it an entirely different way. So they start with the differential form. And then if I take this center node, I'm trying to figure out what the conservation equation is this for the center node. I'm going to integrate that differential form over the neighboring elements. But I'm going to weight that by a weighting function here, W. So essentially what that means is material further away from the node, I don't give as much importance to as the material closest to the node. And then I'm going to integrate that over the volume. So not around the surfaces, but directly over the volume. So once again, this is a different philosophy to how you solve these equations. But for simple solid mechanics problems, they actually give exactly the same discretization. All three methods. So the finite volume method for solids in a nutshell. So I'm just going to review many of the different approaches that have been adopted to date for doing this. So if we start with our governing equation, conservation momentum, and just for simplicity here, I'm going to ignore inertia. I'm going to adopt a Lagrangian approach, so these two terms are zero, and I'm going to ignore gravity as well. So I just have the divergence of stress equals zero. So basically this is Newton's second law for steady state. The sum of all surface forces equals zero. So if I sum around the surface of any cell, I'm going to try and force that to be zero. If I sub in my definition of an ideal solid, a Hookean solid, it might look something like that, where I've written it in the typical, let's say, Newtonian form. But we don't normally write it that way in solids. We'll define pressure in terms of the gradient of displacement. So we often write it this way in terms of our, not viscosity, but a shear modulus. And this is called the first Lemay parameter related to the bulk modulus.
So we're going to apply this equation to each cell in our mesh. So when we go to do that, there are a number of decisions we have to make. So we have to decide on the grid arrangement and how we're going to approximate the force at each face, and how, if needed, we need to stabilize our discretization, and then how we're going to actually solve the equations at the end. So based on these points, in literature, a number of different avenues have been followed for each point, and this has led to a variety of formulations. So I'm going to briefly touch on each one. So the one that we're most familiar with in OpenFOAM is the cell-centered formulation. So we integrate over a cell in our primary mesh, and we store our unknowns at the center or the centroid of these cells. Also popular is the vertex-centered approach. So around each vertex in our primary mesh, we construct a control volume. And there's different ways to do that. And in this case, I'm connecting the centers of the primary mesh with the centers of the faces, and that creates your control volumes. But you can also have vertex-centered overlapping domains. So in that case, for each vertex in the primary mesh, I just take the cells surrounding that and I integrate over those cells directly. So rather than constructing a secondary mesh, I just use the primary mesh directly. So there's examples here. Also less popular now is the staggered grid method. So the staggered grid method essentially is limited to structured meshes, and it's less popular now, but it can also be applied. But if you're integrating in the Y direction, you might construct control volumes around the Y facing faces. And then similarly in the X direction, when you're constructing the X component of your momentum equation, you would use different control volumes. So you use different control volumes depending on which direction you're integrating your equations. Some observations we can make about these different grid arrangements. So the staggered grid, it's not trivial, or maybe it's not impossible to apply to a non-structured grid. So really this has fallen out of favor unless you're looking at maybe problems that can be defined on simple block meshes. So for example, maybe DNS and CFD are represented volume elements in solid mechanics. Also, stress boundary conditions are not trivial at the wall to apply. Looking at the vertex-centered approach, where there's no overlapping domains, the cell centroid and the computational node may not actually coincide. So if I look at this cell here, the node is here in green, but the centroid of this volume is here. So you're not actually directly storing quantities at the centroid. And so this has implications for the order of accuracy of your volume integrals. So it reduces them in essence. Also for vertex-centered methods, you may end up with non-convex cells that you're integrating around. This may or may not be a problem, but the way you calculate or integrate the force around the surface, we'll need to take that into account. So maybe there are limitations of the vertex-centered method, but one good thing is the vertex-centered method actually has nodes on the boundary itself. So you directly store unknowns on the boundary and you directly solve for the displacements or velocities on the boundary. So this is particularly convenient for implementing complex boundary conditions such as stress conditions, applying a force, which we do in solid mechanics. In contrast, the cell-centered method, like in OpenFOAM, our unknowns are all the cell centers, so we don't directly have unknowns on the boundary itself. This makes it difficult to write a function of, for force, which on the boundary, which is a function of the gradient along and perpendicular to the boundary. I have some experience with this, and in Solids for Foam, I shared a method where I introduce phase centers as unknowns on the boundary to overcome this. But this is a bit tedious, so it might be interesting to examine the vertex-centered approach as well. Then for vertex-centered overlapping domains, the integration domains partially overlap for neighboring computational nodes. So that means when I'm integrating around this node, I take this control volume, whereas when I integrate around this node, you can see that I take this control volume, so they overlap. So you might think that's a bit strange, but that's what the finite element method does. The finite element method will have overlapping domains by default. So it's actually not that strange to do it like that. However, the difference is in the finite element method, we integrate the equations over the volume of these cells or into the area. Whereas in the finite volume method, we really go around the boundary. So for overlapping domains in finite volume, that might be a bit inconvenient, because if we want to integrate the force along this boundary here, that will be a function of the, say, the displacements or velocities at these points, but also probably this point here and this point, and probably these points as well. So your computational stencil may become quite large in that case. If we then go on to talk about approximating the force at a face, there are a variety of ways to do that. In the same way in finite element, there are a variety of ways to integrate the force over the volume in terms of different element types. In the same way in finite volume, we have different ways to approximate the forces at the face. So we might be able to do that in terms of just the point neighbors using a compact stencil, or maybe more traditionally in OpenFOAM, we might use second neighbors as well, and for a less compact stencil. And there are very, very many variations on this presented in literature. So for example, when you go to unstructured meshes, you may need to decompose the non-flat faces into triangles. You could use face or point Gauss methods. You might apply skew corrections or second order corrections. And there's also these Godot approaches, or there's even higher ordered methods presented for quadratic or higher ordered finite volume methods. Also, you can use shape functions. So sometimes people get confused and think shape functions is specific to the finite element method, but it's not. It's a key feature of the finite element method, but it is independent of the finite element method. So you can use shape functions inside the finite volume method. So how do they work? So for example, it's easiest to understand if I take the non-overlapping vertex-centered approach. So let's imagine here's the on-node and the unknown node. So this blue region I want to integrate over this. This is my control volume over the boundary. So what we do is, in this primary mesh cell, in this primary grid, I say that the displacement in this cell is described by some function of the displacement at these four nodes. So U0, U1, U2, U3. So I'm going to say the displacement within that cell is a function of those and of the coordinate. So pretty reasonable. So that function is the shape, essentially is the shape function. That's all the shape function is. So if I have that function, then I can easily just calculate what the gradient of the displacement is at the center of these two subfaces. And hence I can approximate the force, and I can integrate over these two faces. And I can do the same in these four primary mesh cells, and that lets me integrate over this control volume as a function of the displacement in these 9 nodes. So that's the concept of shape functions. So even though that's typically not applied in the cell-centered method, like in OpenFOAM, it could be applied. And it has been applied in the vertex-centered method. Once we formed our discretization, it may or may not be unstable. So what do I mean by unstable? I mean that you may get unphysical oscillations in your solution, in your discretized equations. So for example, you're probably familiar with so-called checkerboarding pressure instabilities. So this same thing can happen in solid mechanics, finite volume solid mechanics. So here's a problem where I was performing a large elastoplastic strain analysis of squashing a piece of metal, and we got these numerical oscillations, twice the frequency of the grid. But the same thing happens in other related numerical methods. So finite element method has the same instability issue. So there's different forms. One common form is known as hourglassing. So if you're ever doing an FEA analysis and your grid looks like this, this is an equivalent to checkerboarding. So what happens is when you form your discretized equations, there's certain ways the displacements or velocities can move in certain combinations that do not generate any force, or do not generate any energy, and they're not constrained essentially. So they may appear during the solution, and there's nothing trying to stop them. So there are a variety of different techniques to overcoming these. And there's different types of discretizations that may not be as susceptible. So OpenFOAM, you may have heard, OpenFOAM uses a Ree-Chow-esque or a Ree-Chow-inspired approach. So what that means is OpenFOAM typically in your simple foam or PiezoFoam doesn't use Ree-Chow. It uses a similar concept that doesn't directly require a stabilization term, which is great.
But the true reach out approach is actually adding a term or two terms to your pressure or momentum equation to kill these oscillations. So the original reach out approach basically adds the difference between a Laplacian and the divergence of a gradient. So mathematically, these terms cancel out exactly, but numerically, the divergence of a gradient is a large stencil and the Laplacian is a small stencil. And the difference between them is a small bit of diffusion, like a smoothing term. And then we scale that by viscosity or by some mechanical property and some stiffness, and maybe a user scaling tuning function as well. And then we add that to our governing equation. And we do that in solids. There's also Jameson-Schmidt-Turkle, which basically takes the Laplacian of your velocity or displacement field, and then that's a measure of any high frequency oscillations, and then we'll add a diffusion term proportional to that. And similarly, in reduced finite element integration approaches, they add similar terms to this, and they call it hourglass control or approaches like that. We still need to decide on whether to use an explicit or an implicit algorithm. So once we discretize our equations, I've reintroduced the temporal term here. So m means the new time, m minus 1 means the old time. So then for the divergence of stress, do we calculate all of that at the old time? So that would be explicit, or do we calculate it all at the new time, and that would be implicit? And then if we do an implicit, we can have a segregated approach or a coupled approach, or somewhere in between, a semi-coupled approach. And here's just examples of comparing a pressure wave traveling across a solid plate using an explicit approach and an implicit approach. And each of these have their own numerical characteristics. So explicit approaches, like this red wave here, they tend to introduce dispersion errors, i.e. oscillations, whereas implicit approaches, the blue one, introduce diffusion errors, where they tend to smooth things. And if you have a bigger time step, it gets even worse. So you have to control that in some way as well. So that's maybe some of the technicalities. I'm now going to just briefly look at some of the early publications and some of the original ideas people had to define a volume method for solid mechanics. So the first reported application was in 1988 by Demircic, Martinovic, and Ivankovic, and it was published in Croatian. So my Croatian is not so good, but you could probably guess it's numerical simulation of thermodeformation processes. But Google Translate tells me that it's numerical simulation of thermodeformation processes in a welded piece. So that gives you some motivation of why people looked at finite volume method for solid mechanics originally. So when it comes to things like solidification and welding, it's not so clear how to apply traditional solid mechanics approaches, because it's now overlapping between fluid mechanics and solid mechanics. Later, this was extended. So in 95, this was extended to a fully polyhedral mesh. And the original publication, the OpenFOAM paper, which Gavin was an author on, did have a case presenting a solid mechanics analysis. And the solution method they used there very much closely followed the approach of Demircic and co-workers for the solid mechanics analysis. In contrast, at a similar time, so in early 91, Fryer et al. Introduced this concept of a vertex-centered method using shape functions. And the limitation of shape functions is you have to define these functions explicitly for certain shape cells. So if you have a square or a quadrilateral, you have shape functions for a quadrilateral, whereas you have different shape functions for a triangle. And so that means that you can't easily deal with polyhedral meshes. This is from Thames Polytechnic. I had to, before the talk, actually look up where this university is. So it's actually called University of Greenwich, and they changed the name. Many of you might know the late Professor Zenkiewicz and also Professor Anate. And they also, in the early 90s, looked at the finite volume method for structural mechanics. This particular paper takes a very much a finite element perspective. So they were looking at these weighting functions. So in finite volume method, we don't have weighting functions, but another way to say that from a finite element perspective is the weighting functions are 1. We're multiplying by 1 for the volume. So they were comparing the differences between these weighting functions and the standard Galerich and finite element approach.
Interestingly as well, an early publication using the Phoenix software, which came from the work of Spalding. So by Professor Beale, who's still who's part of the OpenFOAM community now. He looked at a novel way where if you compare solid mechanics with creeping flow and this analogy of stream functions and stress functions, or so-called Airy stress functions in solid mechanics, you can directly solve for this potential in terms of this biharmonic equation. And then from that, you can calculate the stresses. So he showed it worked, but there would be a lot of challenges to get this working in a general 3D unstructured manner, but definitely an interesting approach. And then finally, early in the 90s as well, from Trangenstein, from Lawrence Livermore, they were interested in these compressible Godunov type approaches. So think about things like explosions. So they recast the governing equations in terms of a set of first order partial differential equations. So they directly solve for velocity and deformation gradient, which you may not be familiar with, but essentially it's like solving for the gradient of velocity. So they did it fully explicitly, and if you're familiar with solvers like row central foam, it's a very similar concept. Okay, for the last few minutes of the talk, I'm going to just look at some example cases from some work I've been doing using solvers for foam, using the cell-centered method in OpenFOAM. So here's an example of a heated pressure vessel. So it's just it's hot inside and a high pressure inside. This is a benchmark case. And you can check as you refine the mesh that it approaches benchmark solutions, and you can compare it with commercial finite element softwares and check you get similar answers. Also, you can check the scaling. So in this case, I used a few million cells, I think, and I tried to scale up to, I think it was 800 cores, and the scaling worked pretty well. So solid mechanics doesn't break any of the underlying OpenFOAM scaling. Similarly, you can look at contact mechanics, and one interesting thing is most finite volume methods will give you second order convergence of stresses, and that's not a given in the finite element method. You can do it, but it's often not the case. So that's one nice advantage. So in solid mechanics, I'm giving a solids for foam training later, and there's lots of tutorials included, so you can come and play with some of those. From my own research perspective, I haven't talked too much about the specific details, but one piece of work, a long-standing project I have is with a Belgian multinational steel manufacturer, and I helped them use OpenFOAM to model some of their metal forming processes. Here's just a nice video to end on. I think this case is proposed in literature. I'm not sure what it's called. It's like filling a plastic bag with water. So this is done in solvers for foam, so you can generate nice, colorful pictures as well. So just to end on the outlook, apart from technical obstacles in terms of the finite volume method for solid mechanics, which I find interesting to work on, some of the real main challenges are awareness. Most people aren't even aware you can use any other method rather than finite element method for solid mechanics, and which is obviously not the case. And also benchmarking. If people are to use it, you really want to have publicly available benchmarks showing that these methods or approaches can produce equivalent or better solutions to what's currently available. And as part of this code dissemination is important, because many people will publish and then they don't share their code, so it's very difficult to reproduce what exactly they did. So that's a good place to finish. Thanks very much.
Thank you very much, Philip.